The planet beneath your feet is no longer behaving the way it should, not in some distant, geological, over millions of years sense, but measurably, documentably, right now. And the people whose job it is to track these things are paying very close attention. Most people, if you ask them, will tell you that Earth's rotation is essentially stable, that the small variations scientists occasionally measure are just noise in the signal, the kind of thing that irons itself out and ultimately means nothing. That explanation sounds reasonable. It sounds like the kind of thing that just happens with a spinning planet orbiting a star for 4 billion years. The truth is almost precisely the opposite. The acceleration is real, the core is in motion, and the shield that has protected life on this surface for longer than animals have existed is weakening in ways that are difficult to dismiss as coincidence. And understanding why any of that matters requires going considerably deeper than most people expect. Before we start, if you enjoy exploring the universe with us, a quiet subscribe helps this channel reach further. Now, settle in and get yourself comfortable. Let's begin. On June 29, 2022, Earth completed one full rotation in less time than it ever has in recorded history. No announcement, no warning, no breaking news alert. The planet simply spun faster than any instrument had ever measured it spinning before, by 1.59 milliseconds. And if your first instinct is to hear that number and feel nothing, to file it away as a rounding error too small to matter, that instinct is exactly what this section is going to dismantle piece by piece. Because understanding why 1.59 milliseconds is alarming requires understanding what it overturned. And what it overturned is 4 billion years of consistent, measurable, uninterrupted history going in exactly the opposite direction. Here is what makes this genuinely strange. For as long as this planet has existed, its rotation has been slowing down, gradually, consistently, in one direction. The mechanism responsible for this is the Moon, and the way to understand what the Moon has been doing to Earth for 4 billion years is to picture a break. Not a sudden, catastrophic break, but something patient and relentless. A gravitational hand resting lightly on a spinning wheel, always pulling against the direction of rotation, never lifting, never pausing. Every time the Moon's gravity raises a tidal bulge in Earth's oceans, that bulge wants to stay aligned with the Moon, but the planet beneath it is spinning faster than the Moon orbits, so the bulge gets dragged forward, and dragging it takes energy, and that energy comes out of the planet's rotation. This has been happening every single day for 4 billion years. The days on early Earth were only about 6 hours long, and the Moon's patient, unrelenting friction has been stretching those days out ever since, adding roughly 2 milliseconds to the length of a day every single century. A 2 milliseconds per century sounds insignificant until you let the time accumulate. 4 billion years of that process, 4 billion years of the same mechanism, pulling in the same direction, never stopping. If you tried to count the individual days that have passed since Earth formed, and you counted one per second without ever sleeping, it would take you more than 126 years just to count them. That is the scale of consistency we are describing. The trend towards slower rotation is not a recent pattern or a temporary phase. It is one of the most stable directional processes in the entire history of the planet, woven into the physical relationship between Earth and its nearest neighbor in a way that nothing on the surface could reasonably be expected to interrupt. And yet the evidence that it was interrupted is not theoretical. It is literally written in stone. In ancient coral fossils, roughly 400 million years old, biologists and paleontologists found something that required a second look. Corals grow in daily rings, the way trees grow in annual rings, and the number of rings preserved within a single yearly band tells you how many days were in that year. When scientists examined these fossils carefully, they found approximately 413 daily rings per year, sometimes more, which means that 400 million years ago, the year did not contain 365 days. It contained over 400. The days were shorter. The planet was spinning faster, and from that point forward, the Moon's friction did its work, slowly and inexorably, stretching each day longer and longer over geological time. carrying Earth toward the rotation rate we consider normal today. That is not an estimate or an inference. Those ring counts are physical measurements preserved across hundreds of millions of years of geological pressure and heat, waiting to be read. The deceleration trend is real. The moon's role in producing it is real, and both are so thoroughly established that they are among the most confidently stated claims in the entire field of geophysics. So, when data collected from atomic clocks and laser-ranging satellites began suggesting, around 2016, that the trend had quietly reversed, that the days were not getting longer, but shorter, the initial assumption among people paying attention was that something in the measurement must be off, and not dramatically, not in a way that announced itself, but measurably, in the kind of way that does not resolve when you run the numbers again. The year 2020 set a new record for the shortest average day since precise timekeeping began. 2021 broke that record. Then 2022 arrived, and on June 29th, the record was shattered in a single rotation, 1.59 milliseconds early, the fastest day ever measured. That sentence deserves a moment, because the scientists who study this did not stop at the record. They did what scientists do, which is to go looking for the most boring possible explanation first, and they found several candidates. Seasonal wobbles, the way Earth's axis shifts slightly as ice redistributes across hemispheres with the seasons, can affect rotation speed. Atmospheric pressure changes can do the same thing, as air masses move from one part of the globe to another and alter the planet's moment of inertia the way a spinning figure skater changes speed by moving their arms. Ice melt patterns, shifts in ocean circulation, the atmospheric oscillations driven by El Niño cycles. All of these are real, documented, quantifiable influences on Earth's rotation rate, and all of them were stripped out of the data with the kind of methodical rigor that takes months and multiple independent research groups to complete. What remained after all of those surface factors were accounted for was not zero. The acceleration did not disappear when you removed everything you understood. What remained was a residual, a component of the acceleration that survived every correction, every subtraction, every known surface mechanism applied to it. And that residual is the most important word in everything I have said so far, because a residual, by definition, is what you cannot explain. It is not noise. It is not seasonal wobble. It is not El Niño. It is what is left when you have subtracted all of that and something is still there, still pushing the planet faster, with no complete surface explanation for why. 1.59 milliseconds. It sounds like nothing. So why are engineers at Google, Meta, and Amazon losing sleep over it? The answer is that 1.59 milliseconds is not a number that belongs to human experience. It is a number that belongs to infrastructure, and the two things operate on entirely different tolerances. When you try to feel 1.59 milliseconds, when you try to imagine what that duration is like in lived terms, you cannot, because it is genuinely beneath the floor of human perception. You cannot blink that fast. You cannot react to something that happens in that window of time. Your nervous system is simply not built to register intervals that small, and so the intuitive response is exactly the one most people have, which is to file the number away as technically interesting but practically irrelevant. The problem is that the critical systems your life depends on every single day are not built the way your nervous system is built. They are built for tolerances 1,000 times tighter than anything you can perceive, and they were all designed around one shared assumption, that the planet's rotation is something they can predict. Take the global positioning system. The constellation of satellites that GPS depends on does not actually measure where you are by tracking the planet's spin. It measures time. Each satellite carries atomic clocks and broadcasts a continuous signal that says, in effect, here is the exact moment this signal left me. Your receiver catches those signals from multiple satellites, computes the tiny differences in arrival times, and from those differences triangulates your position. The mathematics involved is extraordinary in its precision, and the entire architecture of it requires that the satellite positions be known to within fractions of a meter at every moment of every day. Yeah, but those satellite positions are computed using reference frames that have to reconcile two different clocks: atomic time, which runs at a constant rate and drifts from planetary spin over years, and universal coordinated time, which is supposed to represent what the Earth is actually doing. When the planet unexpectedly completes a rotation faster than the models anticipated, the gap between where the satellites are predicted to be and where they actually are in relation to the surface introduces errors. Not catastrophic, dramatic errors. Small ones. A few centimeters in ordinary conditions, scaling toward a few meters under the kind of compounding mismatch that builds when the anomaly is not quickly corrected. And a few meters is the difference between a navigation system that puts you on the correct road and one that puts you in the median. For a car, that is an embarrassment. For an autonomous vehicle, it is a collision. For a precision-guided system, it is a miss. The tolerance was always built around a predictable planet. Consider what that kind of timing demand looks like when the stakes stop being navigation and become money. The global financial system, not the abstract concept of it, but the actual infrastructure of exchanges in London and New York and Hong Kong, runs on timestamps accurate to the microsecond. 1 microsecond is 1/1,000,000th of a second. When a high-frequency trading firm executes an order, the timestamp attached to that order is not a convenience. It is a legal instrument. In disputes between firms about who moved first, who had priority, who bears liability for a transaction that went wrong, the resolution comes down to the timestamp record. And the timestamp record is only meaningful if every machine in the chain agrees on what time it is. The exposure created by even 1 microsecond of ambiguity across a contested order in a volatile market is not theoretical. It has been litigated. It has cost firms real money. The entire edifice of financial accountability rests on the assumption that time is a shared fact, that clocks everywhere agree, that they agree because they are all anchored to the same master reference, and that the master reference is stable. When the planet accelerates by 1.59 milliseconds in a single rotation, it is not directly causing a microsecond of ambiguity, but it is stressing the reconciliation layer between atomic time and planetary time. And every stress on that layer propagates through every system downstream that depends on it. 1 microsecond of ambiguity can represent millions of dollars of legal exposure in a single disputed order on a single volatile afternoon. That is not a metaphor. That is a measurement. Then consider the power grid. The electrical current supplied to your home or office runs at either 50 or 60 cycles per second. 50 Hz across most of the world. 60 Hz in North America. That frequency is not a suggestion. It is a physical property of alternating current, and every motor, every transformer, every piece of industrial equipment connected to the grid is engineered to match it. Yet the grid operators, the utilities, and the interconnected systems that maintain the flow of power across entire continents actively monitor frequency at every moment of every day, and they have systems that compensate when generation and demand drift apart. A grid that falls below frequency for too long starts damaging equipment. A grid that rises above it creates different, equally serious problems. And the reference against which frequency is ultimately calibrated is time. Grid operators use precision time signals to synchronize across vast distances, to coordinate the phase of current flowing from one region to another, to ensure that power moving from a generator in one state to a load in another state is arriving in alignment rather than in opposition. When the planetary reference that underpins precision time develops anomalies, the correction mechanisms built into the grid have to work harder. The system does not fail immediately, but it is like threading a cargo ship through a narrow strait at night. The ship is enormous, the channel is deep enough, and a skilled pilot can manage the passage. But if the navigation charts are wrong by even a small amount, and the current is slightly unpredictable, and the passage is long, the margins that were comfortable become margins that are merely adequate, and the margins that were adequate can become margins that are not enough. And then there are the systems where the stakes are not money or navigation, but the continuation of a human life. Hospital linear accelerators, the machines used in radiation therapy to direct concentrated beams of radiation at tumors, coordinate their delivery with the patient's breathing cycle. A tumor inside a lung moves as the lung expands and contracts, and the system that targets it tracks that movement in order to concentrate the dose on the tumor and minimize exposure to the surrounding tissue. The timing tolerances involved in that coordination are measured in fractions of a second. None of that system is directly controlled by planetary spin in a way that would immediately fail if Earth ran a millisecond fast. But every one of those systems relies on a network of synchronized clocks, and every synchronized clock in every hospital is part of the same global timekeeping architecture that is now navigating an anomaly. It was not originally designed to absorb. The point is not that patients are in immediate danger this afternoon. The point is that the engineering assumption running through every one of these systems, GPS, financial exchanges, power grids, hospital timing networks, is the same assumption, expressed in different forms, in different industries, in different languages, on every continent. That assumption is that the planet will behave the way it has always behaved, and that the models built to predict its behavior will remain accurate. The millisecond is not the problem. The loss of predictability is the problem. In 1972, the world quietly agreed on a patch, not a solution. A patch, and the answer starts with a clock, not the kind on your phone, and not the mechanical pendulum clocks that served civilization for centuries before anyone thought to question whether they were accurate enough to matter. Before 1955, the best available timekeeping instruments were accurate to about 1 second per 300 years. Take a moment to hold that. 300 years of running, and the total accumulated error across that entire span, the full weight of 3 centuries, was 1 second. By the standards of daily life, that is a number so precise it hardly seems worth improving. You could set a clock in 1600 and leave it running without any adjustment, and in 1900 it would still tell you, with 1 second of accumulated drift, what time it was. That sounds like mastery, and it sounds like the problem was essentially solved. And then cesium changed everything. Cesium-133, a specific isotope of a soft silvery metal, oscillates at a frequency that can be measured and that does not change. Not approximately, not on average. The number of oscillations per second is 9,192,631,770. Exactly, not a rounded figure, not an estimated derived from repeated measurement. That number is the definition of a second, written into international standards as the exact number of cycles of cesium-133 radiation that constitute 1 second of time. And an atomic clock built around that oscillation loses or gains 1 second per 300 million years. And the improvement from the best pre-atomic clock to an atomic clock is not incremental. It is not even a large step forward. It is the difference between measuring the distance from your front door to the corner of your street and measuring the diameter of a hydrogen atom. Both are measurements of length, but one of them belongs to a different order of reality entirely. 300 years to accumulate 1 second of error. 300 million years to accumulate 1 second of error. If that previous clock were running since the first multicellular organisms appeared on Earth, it would be wrong today by about 1 second. The cesium clock would need to run from the formation of the solar system to the present, and then 4 additional solar system lifetimes beyond that, before its accumulated error reached a full second. And that is the gap between the instruments that came before and the instruments we are talking about now. So when those instruments, built to that standard, running to that precision, began reporting anomalies in the length of the day, the obvious move was to ask whether the instruments themselves might be wrong. It is a reasonable question. It is the question a careful person asks. You cannot measure a planet with a ruler that bends, and if the ruler has never been tested against something truly fixed, then every measurement it produces is suspect, however confident it looks on the printout. That instinct, to question the instrument before accepting what it tells you, is exactly correct. It is also exactly where this particular line of reasoning collapses, because the atomic clocks were not the only instruments watching, as the other tool is called very long baseline interferometry, and the phrase matters less than what it actually does. Radio telescopes positioned on multiple continents, separated by thousands of kilometers, simultaneously observe the same extremely distant sources of radio emission: quasars, active galactic nuclei, objects so far from Earth that they are measured not in light years but in billions of light years. At those distances, the apparent position of a quasar in the sky does not change as Earth moves. They are so remote that the parallax effect, the shift in apparent position that happens when you observe something from two different locations, is functionally zero for these objects. They are, for all practical purposes of measurement, fixed points embedded in the cosmos at a distance so vast that Earth's motion around the Sun does not even register as a detectable wobble when you are looking back at us from there. And by measuring the precise moment at which a signal from the same quasar arrives at each telescope on the ground, you can calculate, to extraordinary precision, the orientation of Earth in space. Not the orientation estimated from a model, the actual, measured orientation derived from objects that have no relationship whatsoever to Earth's surface, Earth's atmosphere, Earth's spin, or any of the systems that might conceivably introduce a bias into measurements made from within those systems. You are not measuring Earth with Earth. You are measuring Earth with the universe. The organization that compiles this data and publishes the results is the International Earth Rotation and Reference Systems Service, based in Paris. Every few days, the IERS releases updated Earth orientation parameters, the precise values describing how Earth is positioned, how it is wobbling, and how its rotation rate compares to atomic time. Those publications are built from multiple independent data streams: atomic clocks, very long baseline interferometry, and additional satellite tracking systems, all cross-referenced against one another. The instruments are running and they agree. Not one instrument, reporting one number, which could conceivably reflect a local error or a calibration drift, or any of a dozen technical explanations. All of them, simultaneously, from different continents, using different physical principles, and measuring different aspects of the same phenomenon, arriving at the same conclusion. And that conclusion revealed something worth sitting with for a moment, because there is something almost philosophical about it. For centuries, clocks were compared against the sky. Earth's rotation was the reference. A second was 1/86,400th of the time it took the Earth to rotate once. That was not a metaphor. That was the definition, written into scientific standards, because the planet was assumed to be the most reliable timekeeper available, and everything else, every clock, every instrument, every calendar, was calibrated against its spin. Then, atomic clocks came along and quietly revealed that Earth was never a reliable standard at all. The planet was always drifting. Its rotation sped up and slowed down in response to things happening on and inside it. And for centuries that drift went undetected because the instruments used to measure it were themselves compared against the very thing they were supposed to be measuring. If your clock is always right, perfectly, absolutely, unchangeably right, but the world around it starts drifting out of sync, who exactly is wrong? The answer, once the atomic clocks arrived, was unambiguous. The planet was the anomaly, not the clocks. And the clocks were sensitive enough to prove it in ways that make the case impossible to dismiss. The El Niño events of 1982 to 83 and 1997 to 98 are both visible in the rotation data, the redistribution of water mass across the Pacific, yet the shifts in atmospheric pressure and wind patterns, each one leaving a detectable signature in the length of the day, each one confirming that even large-scale weather systems carry enough angular momentum to alter how fast Earth spins. And when the earthquake struck off the coast of Sumatra in December 2004, one of the most powerful seismic events in recorded history, the redistribution of mass as the seafloor shifted and the planet's shape changed, ever so slightly shortened the length of the day by approximately 2.68 microseconds. Not a number estimated from a model after the fact, a number read directly from instruments that were running at the time, comparing atomic time to planetary rotation, and catching the signature of a geological catastrophe in the fractional lengthening and shortening of a single day. A figure skater who extends both arms slows her spin as her mass moves outward. A figure skater who pulls her arms in tight spins faster as her mass redistributes closer to her axis. The earthquake pulled a small amount of Earth's mass fractionally inward, and Earth responded exactly the way that physics requires. It spun a little faster, and the instruments caught it. This is the thing that forecloses the measurement error explanation entirely. A system sensitive enough to detect the 2.68 microsecond signature of a single earthquake, verified against fixed points billions of light years away, are confirmed by independent institutions publishing their results every few days. That system is not producing noise when it tells you that Earth's rotation is accelerating. When atomic clocks and Earth began contradicting each other, humanity built a workaround in 1972, and that fix, deployed quietly, used over 27 times in the decades since, written into the foundations of digital infrastructure without most of the people who depend on it ever knowing it exists, may now be the most dangerous piece of infrastructure in the global digital system. The fix that came out of 1972 sounds, on first description, like something sensible. When atomic time and Earth time drifted too far apart, more than 9/10 of a second, a single second would be inserted into the global timescale, slipping into the calendar like a quiet adjustment, invisible to most people, handled by the systems that handle such things, and then gone. A leap second. The idea was that you could keep atomic time and planetary time roughly synchronized by simply adding a moment when needed, the way you might add a drop of water to a scale to bring it back into balance. 27 times since 1972, that adjustment has been made. 27 leap seconds inserted into the official global timescale over roughly 5 decades. And every single one of them has been positive. Every single insertion has moved the clock forward, adding time, because the Earth throughout that entire period was spinning more slowly than atomic clocks expected, dragging slightly behind, requiring the calendar to be padded to keep pace. The same direction, every time, for more than 50 years. The significance of that uniformity will become clear in a moment. But first, consider what happened in 2012 when a positive leap second was deployed. A positive leap second means that at the moment of insertion, the clock reads 23 hours, 59 minutes, and 60 seconds before rolling over to midnight. An extra second, a moment of extended time moving forward slightly more slowly than expected before continuing as normal. This is the friendly direction, if any direction can be called friendly. A direction every system was at least theoretically designed to handle, because time moving forward, even in a slightly unusual way, is what every operating system, every network protocol, every database was fundamentally built around. Time goes forward. Its systems were written to expect that. And still, when the 2012 leap second was deployed, Reddit went down. LinkedIn experienced cascading failures. Qantas Airlines, one of the largest carriers in the Southern Hemisphere, had significant portions of its check-in and operations systems fail, leaving passengers stranded at airports while engineers worked to recover the infrastructure. None of those failures were the result of time moving backward. They were the result of time moving forward in a slightly unexpected pattern, a single additional second that certain internal clocks and schedulers were not designed to accommodate cleanly, and the consequence was real disruption, visible to ordinary people, measured in delayed flights and failed logins and server outages across multiple continents. That was the good direction. Yes, the thing that makes this genuinely unsettling is what the alternative looks like. Because if Earth's rotation continues to accelerate, as the data from 2016 onward has been quietly, persistently suggesting, then eventually the planet will be spinning fast enough that atomic clocks will be running behind it rather than ahead of it, and the correction will need to go the other way, not an added second, a removed one. And what that actually means, in mechanical terms, is that the clock on any given day would move from 23 hours, 59 minutes, and 58 seconds directly to midnight. 23:59:59 would not exist. There would be a gap where that second used to be, a moment the calendar skips entirely, a beat that the planet's spin has outpaced before the timekeepers can account for it, a gap where time used to be. The numbers continue, but one of them is simply absent, and every system that expected to pass through it finds itself, for reasons it cannot immediately diagnose, in an inconsistent state. Network time protocol, the underlying architecture that keeps computers across the internet synchronized with each other, was designed on the assumption that time moves forward, not because the engineers who built it were naive, but because that is how time has always behaved in the context of every system ever deployed. You can build toward an added moment. You can write code that accounts for a slightly longer pause before midnight, but a removed moment is a different category of problem entirely, because it is not an extension of normal behavior. It is a violation of the core assumption that every timer, every scheduler, every timestamp-dependent process was built upon. The clock skips backward relative to expected sequence, and any process that was waiting for a second that no longer arrives is now, depending on how it handles the inconsistency, either frozen, looping, reporting a nonsensical error, or, worst of all, continuing silently with an internal state that is now wrong in ways that will not surface immediately. Meta, the company behind Facebook and Instagram, and the infrastructure that handles more simultaneous user interactions per second than most governments process in a day, published a formal paper on this scenario. Their language was not alarmist. It was technical and measured, and it described a negative leap second as an event with devastating effect on software relying on timers or schedulers. And that word, devastating, in a technical paper from an engineering team at that scale, is not rhetorical. It is a damage assessment. Google, Amazon, and Microsoft each concluded that the existing system could not be trusted to handle the event cleanly, and each one independently developed its own alternative, a method called time smearing, in which the adjustment is spread across a longer window, hours, rather than a single inserted or deleted second, so that no individual moment contains the full discontinuity. 3 of the largest technology companies in the world built 3 different custom solutions to a problem that the official system was not equipped to handle. The fact that their solutions differ from each other is itself informative, because it means there is no consensus answer, only 3 separate engineering bets on which approach will fail least badly. And then there is the financial dimension, which is where the word genuinely unsettling stops feeling like emphasis and starts feeling like understatement. Regulatory bodies around the world require that financial transactions be recorded with timestamps accurate to the microsecond. A full second of backward movement does not create confusion. It creates liability. It creates a window in which 2 transactions can carry the same timestamp, in which the sequence of events that determines which trade was placed first, and therefore which counterparty bears the risk of a price movement, becomes legally ambiguous. The Bank for International Settlements, which functions as the central bank for central banks and sits at the structural center of global interbank settlement, commissioned a formal model of what a negative leap second event would do to interbank payments. The results of that model were classified as sensitive financial information and have not been released publicly. The classification itself is informative. If the modeling had shown that systems would handle it gracefully, there would be no reason to suppress the results. You release the findings that reassure. You protect the findings that do not. In 2022, the international standards body responsible for global timekeeping voted to eliminate the leap second entirely by 2035. No more insertions, no more deletions, no more patches added to the patch. Atomic time and planetary time will simply be allowed to drift apart, and the accumulated difference will be dealt with at some unspecified future date using some unspecified future method that does not yet exist. That decision defers the problem. It does not resolve it. All of this, the clocks, the leap seconds, the cascading software failures, the classified financial models, the competing engineering solutions from companies large enough to run small countries, is a surface symptom. The thing that is actually driving the acceleration lives somewhere no human instrument has ever physically reached. Imagine drilling straight down, not a real drill. No real drill comes close to what this requires. and we will get to why in a moment. But imagine the journey anyway, and because the place you are trying to reach does not announce itself from the surface, and your mind needs some way to hold the distance. You push through the first few kilometers, through granite and basalt, through the oceanic crust that underlies the seafloor and the thicker continental crust beneath cities and mountain ranges. This layer is the one we have physically sampled, the one geologists have mapped and named and argued over for 2 centuries. And even in its strangeness, it still feels like something solid and knowable, something that belongs to the world you recognize. Then the crust ends, the mantle begins, and you are now in rock that behaves, over geological timescales, more like a very slow fluid than a rigid solid, stone that creeps and convects over millions of years, and that carries heat upward from the interior in gradients so slow that a human lifetime could not measure them. You keep going, 2,000 kilometers, 2,500. The mantle extends nearly 3,000 kilometers from the base of the crust, and every meter of that descent involves pressures and temperatures that increase in ways your body has no vocabulary for. And then, at approximately 2,900 kilometers directly beneath wherever you are standing right now, something changes in a way that is not gradual at all. When did you last think about what is happening that far down? The rock ends, not because it gets hotter, though it does, not because the pressure relents, though nothing in this direction means less pressure. The rock ends because you have crossed a boundary that geophysicists call the core mantle boundary, and on the other side of that boundary, the iron and nickel that make up the outer core are not solid. They are liquid, entirely, completely, continuously liquid. A global ocean of molten metal 2,300 kilometers thick, sitting at temperatures between roughly 4,000 and 5,000 degrees Celsius. That temperature range matters because the surface of the sun that you see when you look up at the sky on a clear afternoon, the photosphere, the visible layer from which sunlight actually reaches you, sits at approximately 5,500 degrees Celsius. The outer core is not dramatically cooler than that. In some zones, it approaches that number closely. Something hotter than the surface of the sun is flowing like liquid 2,900 kilometers directly beneath wherever you are standing. And it has been doing so, without pause, for billions of years. Sit with that distance for a moment. If you drove straight down at highway speed without stopping, without the road dissolving in heat, without the pressure collapsing anything you had arrived in, you would be driving for more than 2 years before you touched the first drop of that iron ocean. 2 years of descent, straight through the planet, before you reached anything that was not rock. And once you were there, it would be dark. Not the darkness of a room with the lights off, or even a cave where the last trace of ambient light fades after the first bend in the tunnel. This is total darkness under pressure that would crush any known material to powder. Darkness in an environment where the concept of human presence is not merely impractical, but physically incoherent. Darkness that has persisted since before the first living cell divided anywhere on Earth's surface. In that darkness, iron and nickel move. Not quickly. The currents in the outer core travel on the order of tens of kilometers per year, which sounds slow until you consider the scale of what is moving. A global ocean of liquid metal thousands of kilometers deep, circulating continuously, carrying heat from the deeper interior outward toward the mantle boundary above. Tens of kilometers per year is not a lazy drift. At that speed, over the span of time, this ocean has existed, as those currents have traced paths that would encircle the Earth thousands of times. And as they move, something happens that is among the more extraordinary physical phenomena occurring on this planet at this moment, or any moment. When electrically conductive fluid moves through an existing magnetic field, it generates electrical current. When electrical current flows, it produces its own magnetic field. And that magnetic field influences the motion of the conductive fluid, which generates more current, which strengthens the field, which shapes the flow. The system feeds itself. It is self-sustaining in a way that has no convenient switch, no external power source, no moment at which it requires outside input to continue. This is the geodynamo, and it is the mechanism by which Earth generates the magnetic shield that has deflected charged solar particles away from the surface for longer than complex life has existed anywhere on the planet. The magnetosphere that protects every living thing from radiation bombardment is not a feature of the crust or the atmosphere. It is a consequence of liquid iron moving in total darkness 2,900 kilometers below your feet. That motion is not static. The currents shift. The circulation patterns in the outer core change over years and decades in ways that ripple outward through the mantle above them, because iron moving in a magnetic field exerts force, and force at that scale does not stay contained at depth. The electromagnetic coupling between the outer core and the mantle means that when the circulation changes, it exerts torque, rotational force transmitted upward through 2,900 kilometers of rock to the surface layer where the clocks are running and the GPS satellites are orbiting, and the atomic time is accumulating its disagreement with planetary time. The European Space Agency operates a constellation of 3 satellites called Swarm, placed in orbit specifically to map Earth's magnetic field continuously and in high resolution, giving researchers a way to infer what the outer core circulation is doing without any instrument ever reaching it. What the Swarm data documented is a change in outer core circulation whose timing aligns with the surface acceleration that began appearing in the rotation measurements around 2016. And the residual, the part of the acceleration that remained after every known surface factor was removed, points not outward to weather or ocean or atmosphere, but inward, toward that iron ocean moving in the dark beneath the entire world. But there is something sitting inside that liquid iron ocean, something that by every instinct should not exist in the form it takes, something sitting inside that liquid iron ocean. That phrase carries a specific weight once you understand what it refers to, because the thing sitting inside the outer core is not what most people picture when they imagine the center of the Earth. Most people carry a rough image of the planet's interior as something like a series of concentric shells, each one denser and hotter than the one above, converging on a central mass that is presumably solid, dense, inert, the way a peach pit is solid and inert relative to the flesh around it. A static object, a weight at the center, something that has simply always been there and does not do very much. That picture is wrong in ways that are genuinely significant, and the degree to which it is wrong has only become fully apparent in the last few decades. The inner core is a sphere of solid iron approximately 2,440 kilometers in diameter. To put that in terms that carry some spatial weight, that is approximately the diameter of the moon. The moon, which you can see on a clear night hanging in the sky, which exerts enough gravitational force to move entire ocean systems across the face of the Earth. That same diameter of material exists as a solid ball of iron sitting at the exact center of the planet, more than 5,000 kilometers below your feet. Every mountain, every ocean floor, every kilometer of crust and mantle and liquid outer core you have already descended through in your imagination. All of that is above it. And that object at the center is genuinely enormous, and it exists in a kind of darkness that has no comparison anywhere on the surface of the Earth. Not merely the darkness of a cave or a deep ocean trench, but the darkness inside the liquid iron outer core, which is itself in total darkness, so that the inner core sits in darkness within darkness, shielded from any conceivable light by thousands of kilometers of molten metal and rock. Now consider what that object is made of, and what conditions are required to keep it in the form it takes. The temperature at the inner core is approximately 5,000 degrees Celsius. At that temperature, iron, the same element, iron, has absolutely no business being solid. The outer core surrounding it, also primarily iron, is somewhere in a similar temperature range, and it is entirely liquid. Iron at 5,000 degrees should be a liquid. Hey, everything about the chemistry of iron at that temperature wants it to be a liquid, and yet the inner core is solid. The reason it is solid is pressure. At the center of the Earth, the weight of every layer above, the mantle, the outer core, the crust, everything, bears down on that central sphere with a pressure that exceeds 3 million times the atmospheric pressure you experience at the surface right now. 3 million times the pressure of the air against your skin as you listen to this. The two forces are balanced at a precise and extraordinary point. The temperature wants to melt the iron, and the pressure refuses to let it melt. And the result is something that should not exist in the form it takes. A solid ball of iron nearly as wide as the moon, sitting in total darkness at the center of the world. You're hotter than the surface of the sun and solid anyway, because the weight of a planet is pressing it together. The way we know this object exists, and the way we have measured its properties, is not through any instrument that has ever come close to reaching it. Nothing built by human hands has descended more than a trivial fraction of the distance to the inner core. What we use instead is seismic waves, the energy released by earthquakes traveling through the Earth's interior and arriving at detector stations on the other side of the planet. Different materials transmit those waves at different speeds, and different states of matter, liquid versus solid, transmit different types of waves entirely. Some wave types cannot propagate through liquid at all. And so when an earthquake occurs on one side of the Earth and the wave patterns recorded on the opposite side show specific signatures, those signatures carry encoded information about what the waves passed through on their way. It is, in a very precise sense, using sound to see inside something you cannot open, the way a doctor uses ultrasound to image tissue that no instrument has touched. Except the object is the entire planet, and the sound is seismic energy from earthquakes, and the image it produces is a map of the deep interior assembled from decades of accumulated wave data. That is how we know the inner core is solid. That is how we know its size. And that, crucially, is how we know something about the inner core that changes everything that has been described in the preceding argument. The inner core rotates, and not just with the rest of the Earth, as you might assume a central mass would, locked in place, rotating in lockstep with the surface because it has nowhere else to go. It rotates independently because it floats inside the liquid outer core the way a ball bearing sits in oil. It is not physically coupled to the layers above it in any rigid sense. The liquid surrounding it allows it to rotate at its own rate, driven by the same electromagnetic forces that drive the outer core circulation, but free to diverge from the surface rotation over time. And what the seismic data from the 1990s showed is that the inner core was over-rotating, spinning faster than the surface by somewhere between 0.3 and 0.5 degrees per year. That sounds like a small number, and if you think of it in terms of a single year, and it is a small number, but over decades, that cumulative divergence adds up to a measurable angular offset between the inner core and the surface above it, and the seismic wave signatures, because waves traveling along different paths through the inner core behave differently depending on its orientation, carry a record of that rotation over time. The data from multiple independent research groups across different seismic networks pointed to the same range, which is the kind of convergence that gives scientists confidence in a result. Then, around 2009 and 2010, something changed. The over-rotation began to slow. The rate at which the inner core was pulling ahead of the surface deceleration showed up first as a subtle shift in the seismic signatures, as then became consistent enough across the data to constitute a finding. In 2023, Yi Yang and Xiaodong Song published their analysis in Nature Geoscience, one of the most significant findings in deep Earth science in several decades, presenting evidence that the inner core had not merely slowed its over-rotation, but may have reversed direction relative to the surface, now rotating slightly more slowly than the surface above it, having passed through a period of deceleration that began in the late 2000 years and continued into the following decade. And here is where the figure skater analogy, introduced much earlier in this argument, becomes not an analogy, but a physical mechanism. When a spinning object slows, the angular momentum it was carrying does not disappear. Angular momentum is conserved. Yet it has to go somewhere. The inner core is not isolated. It is electromagnetically coupled to the liquid outer core surrounding it, and the outer core is coupled to the mantle above it, and the mantle is coupled to the crust. The coupling at each boundary involves a delay, electromagnetic coupling between the inner core and the outer core, mechanical coupling between the outer core and the mantle, the gradual transfer of rotational energy outward through layers that do not respond instantly. That delay, measured in years to decades, is not a flaw in the theory. It is precisely what the theory predicts. And when you look at the timeline, inner core deceleration beginning around 2009 and 2010, coupling delay of years to decades, a surface rotation acceleration becoming measurable in the instruments around 2016, the numbers do not merely overlap in a vague, suggestive way. They align. The momentum from a decelerating iron sphere the size of the Moon, transferring outward through every layer of the planet, arriving at the surface as a measurable increase in rotation rate, more than 5,000 kilometers above where that deceleration began, across a timeline that fits the observed data. That is the mechanism. That is physically grounded. It is supported by independent datasets, and the timeline fits precisely. What does it look like when that energy finally arrives at the surface? That answer is being written at the very top of the world, where hundreds of billions of tons of ice are disappearing every single year. There is a paradox sitting at the center of everything discussed so far, and it begins with the intuition you probably already have, because the physics is actually correct. When a spinning object has mass near its axis and that mass moves outward, the object slows down. A figure skater pulling her arms in spins faster. A figure skater extending her arms outward spins slower. You have heard this analogy twice already in this argument, and the reason it keeps returning is that it describes real physics at every scale, from a human body rotating on ice to a planet rotating around its own axis. And when you apply it to ice loss, the intuition is sound. Ice sitting at the poles is sitting very close to the axis of Earth's rotation. When that ice melts and the water flows into the ocean basins, which spread outward toward the equator, a mass is moving away from the axis. The moment of inertia increases. The planet, like the skater extending her arms, should slow down. That is correct physics. It is the right answer for the long term. The problem is that we are not living in the long term. We are living in the transition. And in the transition, the short-term effects do not simply run ahead of the long-term destination at a reduced pace. They run in the opposite direction. Not a slower version of the outcome, the opposite sign. And to understand why, you have to understand what is happening not just to the ice, but to the rock underneath it. The ice sheets sitting on Greenland and Antarctica have been there, in some form, for millions of years. The rock below them has been bearing that weight for so long that it has deformed, was pressing downward under the load, the way a mattress deforms under a weight left on it for years. When you remove the weight, the mattress does not spring back immediately. It rises slowly, over time, working back toward the shape it held before the load was placed on it. The rock does this too. Geologists call it post-glacial rebound, and it is happening right now, measurably, in Scandinavia, in Canada, in every region where massive ice sheets sat during the last glacial maximum and have since retreated. The rock is still rising, not fast enough to notice in a human lifetime without instruments, but rising at rates that show up clearly in GPS measurements, in some regions by more than a centimeter per year. And rising rock is rock moving back toward the axis, which is the opposite of the ice melt effect. And the moment of inertia decreases in the short term as the crust rebounds, even as the long-term trajectory points the other way. Combine that with the fact that ice loss is not uniform, that Greenland and Antarctica are losing mass at different rates and in different patterns, and that ocean water redistributes through basin geometries that are not symmetric, and you have a system in which the short-term rotational effects are not simply the long-term effects in miniature. They are the transition period, running its own dynamics, and we are inside it. The scale of what is moving is not abstract. Since 2002, two satellites called GRACE, the Gravity Recovery and Climate Experiment, have been measuring mass redistribution on Earth's surface directly, without assumption, without proxy, as pure measurement. Yes, the two satellites fly roughly 220 kilometers apart in the same orbital path, and as they pass over regions of varying mass, the gravitational pull on the leading satellite changes slightly before the trailing satellite reaches the same position. That difference in pull creates a tiny change in the distance between the two satellites, and that change is what Grace measures. The precision of that measurement is smaller than 1/1,000,000th of a millimeter. To appreciate what that means, a single human hair is roughly 70,000 millionths of a millimeter in diameter. Grace is detecting changes in the gap between two satellites that are smaller than the diameter of a single human hair by a factor of 70,000. This is not a system that infers mass movement from secondary effects. It is a direct reading of gravity itself, of mass itself, moving on the surface of the planet. The instruments are running. They have been running for more than 2 decades. What those instruments show for Greenland is a loss of approximately 280 billion tons of ice every single year. That number is difficult to hold. 280 billion tons is not a figure that maps naturally onto anything in ordinary experience, so consider it this way. If you wanted to replace that mass with water, you would need to drain a lake roughly the size of Lake Superior to a depth of several meters every year and pour it into the ocean, not once, every year. And Greenland is doing this continuously, losing that mass to melt and to outlet glaciers carving ice directly into the sea. And the Grace satellites are measuring it not as an estimate extrapolated from surface readings, but as a direct gravitational signature, mass by mass, year by year. Antarctica, simultaneously, is losing approximately 150 billion tons per year through its own combination of surface melt and dynamic ice loss at the margins. Together, these two ice sheets are removing more than 400 billion tons of frozen water from their positions near the axis of the planet and redistributing it across the global ocean every single year. The cause of what is happening at the surface originates in total darkness, in processes deep inside a planet that humans have never visited and cannot visit. But the consequences of those processes arrive at the very top of the world, in ice that has been accumulating for millions of years, and can be measured from orbit. The instruments are running. They do not infer. They measure gravity changing in real time. And the redistribution of that mass is not merely changing how fast the planet rotates. It is changing where the planet's axis points. The geographic North Pole, the point on the surface through which the axis of rotation passes, has always drifted slightly, has always wandered within a range defined by the distribution of mass across the planet. For most of the 20th century, it was drifting slowly in one general direction, at a rate of a few centimeters per year, a motion so gradual that it took precise instrumentation even to detect. Then, around the year 2000, the direction of that drift changed. The pole turned eastward toward Greenland, and the rate at which it was moving accelerated sharply, reaching approximately 17 centimeters per year, several times faster than it had been moving before. The timing of that directional shift corresponds directly with the acceleration of Greenland ice loss. And the mechanism is the same mechanism that governs all of this. Mass redistributed on the surface of a rotating body changes the body's rotational dynamics, including the orientation of the axis through which that rotation occurs. The loss of mass from Greenland is gravitationally significant enough that it has measurably changed where the axis of Earth's rotation is pointing, not over geological time, within a single human lifetime, within the years that most people alive today have been alive. The axis of the planet has moved to a measurably different position than it occupied when most people alive today were born. And something even more fundamental was disappearing at the same time. There is a motion that Earth makes, separate from its rotation, separate from its orbit, separate from the drift of the pole, that has been one of the most reliable features of the planet's behavior for the entire history of precise measurement. It is called the Chandler wobble, and it describes a small oscillation in the orientation of Earth's axis, a slight nodding motion in which the geographic pole traces a rough circle across a period of approximately 14 months. The amplitude of that circle is small, typically a few meters at the pole itself, but the cycle has been consistent enough that when you look at the historical record of precise geodetic observations, you see the same rhythm repeating with the dependability of a heartbeat. 14 months, in every 14 months. Stable enough that researchers came to treat it not as something that needed to be explained in each measurement period, but as a background constant, a permanent feature of the planet's rotational dynamics that you could factor into your calculations and forget about. Between 2000 and 2005, it nearly disappeared. The amplitude of the Chandler wobble during that period dropped to approximately 1/6 of its typical value, which means the wobble did not stop, but it became so suppressed that the familiar rhythm was barely detectable above the noise of measurement. The motion that had repeated reliably for as long as anyone had been precise enough to observe it suddenly lost almost all of its strength, and the mechanism responsible for that suppression remains, and in the most honest language available, genuinely unknown. There are hypotheses involving changes in deep ocean circulation, shifts in how pressure is distributed across the ocean floor, and in the way that mass was moving through the water column at a global scale. And those hypotheses point toward a plausible cause. But the certainty required to say that this is the explanation rather than a contributor to it is not yet there. What the data suggests and what can be confirmed with complete certainty are not the same thing, and that tension between the two is exactly where science lives when it is working on something genuinely difficult. What can be said without hesitation is this: during those 5 years, is something in the ocean circulation changed substantially enough that a fundamental oscillation of the planet's axis was knocked back to 1/6 of its normal amplitude. A force as basic to Earth's rotational behavior as a heartbeat becoming irregular is not a minor anomaly in a peripheral measurement. It is a signal from a system that is not behaving the way it has behaved through the entire span of human civilization. And if the behavior of the ocean is capable of suppressing the Chandler wobble, then the ocean is worth thinking about more carefully in every other context as well, including the one that most people believe they already understand: the question of how the ocean responds to melting ice. There is an image that accompanies this question in most people's minds, and it is an image of a bathtub. Ice melts, yet water flows into the ocean. The level rises the way water rises when you turn on a tap, evenly, gradually, uniformly across the surface. Every coastline experiencing the same increase at the same time. That image is not approximately wrong. It is fundamentally wrong. The reason it is wrong begins with a property of ice sheets that does not come up in most conversations about sea level, which is that an ice sheet as large as Greenland is not merely a mass sitting passively on the landscape. It is a gravitational body. It is large enough to exert a measurable gravitational pull on the ocean water surrounding it, literally drawing that water toward it through the same force that governs the motion of planets. The ocean near Greenland is not sitting at the same level it would occupy if Greenland were not there. It is elevated, pulled uphill toward the ice by gravity, held in place not by any structural feature of the ocean floor, but by the gravitational attraction of hundreds of thousands of cubic kilometers of ice. When that ice melts and the mass begins to decrease, the gravitational pull weakens, and the water that was being held close to Greenland is no longer held there. It flows away. The seas nearest to Greenland, rather than rising as the ice disappears, actually drop, because the force that was drawing them upward is diminishing. The water does not vanish. It redistributes. It moves outward across the ocean, and because of the geometry of that redistribution, the regions that receive the greatest rise in sea level are not the ones closest to the source of the melt. They are the ones farthest away. Tropical coastlines, the equatorial regions, the low-lying shores at the greatest distance from the ice sheets receive a disproportionately large share of the rise. The burden of Greenland's melt does not fall on Greenland's neighbors. It falls on the opposite side of the planet. Every ice sheet has its own gravitational fingerprint, and the pattern of sea level change it produces when it melts is specific to its location, its mass, and its geometry, which means that projecting sea level rise for any given coastline requires knowing not just how much total ice is melting globally, but which ice, from where, at what rate, and how the gravitational redistribution of the released water plays out across the entire ocean surface. The history of this system gives no reason for comfort about how fast that redistribution can happen. Approximately 14,500 years ago, during a period that geologists have named Meltwater Pulse 1A, sea level rose somewhere between 14 and 18 meters over a span of roughly 300 to 500 years, not over tens of thousands of years, over 3 to 5 centuries, which is a period within which entire civilizations have risen and collapsed, a period shorter than the time between the construction of some surviving cathedrals and the present day. 14 to 18 meters is not a rounding error in a projection. It is the difference between a coastline and a seafloor. The planet's oceans have done this before, and the physics that allowed it then is the same physics operating now. And in a world where more than 400 billion tons of ice are leaving their positions near the poles every single year, and the gravitational fingerprint of that departure is being written differently onto every coastline on Earth. If sea level is not rising evenly, then the question of which cities are sitting in a risk zone, far larger than any average, is not a theoretical one. And while the ice shifts and the ocean rearranges, something else is changing, something most people assume is as permanent as the ground itself. The ocean is not a basin waiting to receive what the ice sends it. That framing, as natural as it feels, misses what the ocean actually is, which is a rotating fluid system with its own angular momentum, its own internal currents, and its own ways of exchanging rotational energy with the solid planet beneath it. And the ice story and the ocean story are not sequential. They are simultaneous, and they are entangled in ways that make the combined effect on the planet's rotation considerably more complex than either one alone. When water warms, it expands. This is a physical property so basic that it tends to get mentioned once and moved past. But the rotational implication of thermal expansion has not been fully absorbed into most people's intuition about how the ocean works. The ocean does not warm uniformly. Surface waters warm first and most dramatically. Deep waters warm slowly and at different rates depending on latitude and circulation patterns. When a column of ocean water expands because of rising temperature, the mass of that column does not change. The same water occupies more volume, which means its center of mass rises slightly. And the distribution of that mass within the ocean changes. And because the ocean is sitting on a spinning planet, the spatial redistribution of oceanic mass changes where angular momentum resides within the system. Not by dramatic amounts, not by amounts that would be obvious from the shore, but the ocean covers roughly 70% of the planet's surface. And when a layer of water that wraps most of the globe shifts its effective center of mass upward and outward by even a small amount, the rotational implications accumulate. This is not a theoretical concern at the margins of the calculation. When researchers build the most precise models of Earth's rotation and they cannot account for all of the observed variation using atmospheric and surface data alone, thermal expansion of the ocean column is one of the factors they return to. Yet because the mass redistribution it causes is real, it is ongoing, and it is currently accelerating as ocean temperatures continue to rise. But thermal expansion is the quieter part of the ocean's story right now. The louder part involves a current system that most people have heard of, but few people have thought about in terms of what it actually does for the planet's rotational budget. The Atlantic Meridional Overturning Circulation, which researchers refer to as the AMOC, is a system of deep and surface currents that moves an enormous volume of water through the Atlantic Ocean in a continuous loop, carrying warm surface water from the tropics northward toward Europe and pulling cold, dense water back southward along the ocean floor. It is one of the primary mechanisms by which the ocean distributes heat around the planet, and the data assembled over the past several decades, drawn from ocean temperature records, sediment proxies, and direct current measurements, points towards something that the researchers studying it describe with consistent unease. The AMOC may currently be at its weakest point in more than 1,000 years, not weakening gradually from a stable baseline, already at a low that has not been seen in recorded or reconstructed history going back a millennium. The mechanism driving the weakening is the same meltwater story described earlier, but operating through a different pathway. Fresh water flowing off of Greenland into the North Atlantic is less dense than salt water, and it disrupts the sinking process that drives the deep return leg of the overturning circulation. So when the surface water arriving from the south cannot sink efficiently because fresh meltwater is floating above it, the circulation slows. The ocean's internal conveyor loses speed, and a slower conveyor redistributes mass and momentum within the ocean column differently than a faster one, which feeds back, again, into the rotation of the planet that the ocean is sitting on. And then there are hurricanes, which most people think of as weather events, but which are, among other things, mechanisms of angular momentum, transfer between the ocean surface and the atmosphere above it. Intense storms extract rotational energy from the ocean's upper layers and inject it into the atmosphere in patterns that are neither random nor negligible when summed across a full season. As ocean temperatures rise, the most intense storms become more intense, and not necessarily more frequent, but carrying more energy per storm, which means more momentum transferred per event. The exchanges are happening in a system that is already being reorganized by ice loss, thermal expansion, and a slowing overturning circulation, and the cumulative momentum signal from that reorganization has to go somewhere. It goes into the atmosphere, and this is where the story becomes something different from what most people expect, because the atmosphere is not a passive medium through which these signals pass. It is itself a rotating fluid with mass, and the mass it carries is not trivial. The total mass of the atmosphere is approximately 5.15 times 10 to the 18th kilograms, which is a number that resists casual comparison until you find the right frame for it. The largest mountain ranges on Earth, the Himalayas, the Andes, the Rockies, contain mass in the range of tens of thousands of trillion kilograms. The atmosphere is heavier than every mountain range on the planet combined, by a factor that makes the mountains feel incidental. When the atmosphere shifts how it distributes that mass across latitudes, when its wind patterns accelerate in some regions and slow in others, when the jet streams that circle the planet in the upper troposphere change speed or position, those changes exert a measurable torque on the solid Earth beneath. This is not a metaphor. This is a measurement. In winter, when the jet streams in the northern hemisphere are running at their strongest and the atmospheric angular momentum is concentrated in fast-moving zonal winds at high altitudes, the length of the day increases by approximately 1 millisecond relative to summer. 1 millisecond sounds like nothing until you remember that the infrastructure built on top of atomic timekeeping operates at tolerances, where milliseconds have already caused system failures, and then you realize that the atmosphere is physically pushing and pulling the planet's rotation every time the seasons change, with enough force to measurably shift the length of a day. The Arctic is warming at roughly 2 to 4 times the rate of the global average. That differential warming reduces the temperature gradient between the Arctic and the mid-latitudes, and the jet stream runs on that gradient the way a river runs on elevation. Reduce the gradient and the jet stream weakens and becomes more meandering, tracing longer, more looping paths around the planet rather than the tight, fast westerly bands that characterize a strong temperature contrast. A meandering jet stream redistributes the atmosphere's angular momentum differently across latitudes than a tight one does. The rotational signal that the atmosphere delivers to the solid Earth's surface changes not just in magnitude, but in its geographic pattern, and that change is ongoing and accelerating as the Arctic continues to warm faster than the rest of the planet. In the northern winter of 2015 into 2016, one of the strongest El Niño events on record reorganized atmospheric circulation across the Pacific and beyond, shifting where the atmosphere's mass was concentrated and how fast those concentrations were moving relative to the Earth below. As that event coincides with the period when the surface acceleration that had been present but barely detectable in the rotation data became clearly distinguishable from noise. The signal was already there. The El Niño did not create it, but it may have been the moment when the combined torques from ice, ocean, and atmosphere all aligned in the same direction at the same time, clearly enough that the record they left in the rotation data was unambiguous. This is what the atmosphere is doing in this system. It is receiving signals from the ice sheets as they lose mass and shift the planet's moment of inertia. It is receiving signals from the ocean as thermal expansion redistributes mass and the overturning circulation reorganizes. It is receiving signals from the deep interior, through the magnetic field changes that alter how the core and mantle couple their rotation to the surface. And then it delivers the combined torque of all of those signals directly to the crust of the planet, through friction, through pressure, through the sustained drag of billions of tons of moving air against mountain ranges and ocean surfaces. Every season, every year, in patterns that are not the same as they were a century ago, because the atmosphere itself is not the same. All of these effects are real, measurable, and moving in the same direction at the same time. And there is one more system, one that most people assume is as permanent as gravity itself, that is also changing. The one more system is the magnetic field, and the reason most people treat it as background infrastructure, stable, permanent, yet the kind of thing that simply exists the way gravity exists, is that nothing in an ordinary human lifetime gives you a reason to think otherwise. You cannot feel the magnetic field. You cannot watch it move. The compass needle points roughly north today, the same way it pointed roughly north when your grandparents were born. And that continuity feels like permanence. But permanence and stability are not the same thing. And the difference between them is exactly what the data from the last several decades has been quietly accumulating. Earth's magnetic field is not a perfect shell. It is generated by the motion of electrically conductive liquid iron in the outer core, which means it is not a fixed structure at all, but a continuously produced phenomenon, sustained by a fluid process in the same way that a river current is sustained by gravity and gradient. Change the flow patterns in that fluid, and you change the field that the fluid generates. The field has never been uniform across the planet's surface, and one region in particular has been drawing the attention of every agency that operates satellites in low Earth orbit for decades. It sits over the South Atlantic, stretching roughly from South America toward Africa, and it has a name, the South Atlantic Anomaly. And what makes it remarkable is not just that it exists, but that the field strength there is approximately 40% weaker than you would expect at equivalent latitudes anywhere else on the planet. 40% is not a small variation. When you encounter a 40% deviation in an engineering context, it is not a footnote in a technical report. It is the kind of number that triggers design reviews, that gets flagged in risk assessments, that causes the people responsible for whatever is being measured to examine whether the instrument is faulty before they accept the reading as real. 40% weaker means that the layer of the field responsible for deflecting energetic charged particles from the sun, the particles that, at full field strength, are redirected toward the poles where they produce the auroras rather than penetrating into the lower atmosphere, is substantially thinner over that region, the way that a section of roofing tile worn down to less than half its original thickness is not merely imperfect but functionally compromised in ways that only become visible when the weather changes. And the weather in question, yes, the weather that tests the roof, comes from the sun, every day, without pause. The International Space Station passes through the South Atlantic Anomaly on a regular basis because its orbital inclination carries it across that region of the sky repeatedly during each rotation of the Earth beneath it. And when it does, the station has specific protocols that activate. Electronics that are particularly sensitive to high-energy particle bombardment are placed into protected modes. Certain experiments are paused. Astronauts receive slightly elevated radiation doses during passage. This is not a theoretical concern that engineers flagged during design reviews and then set aside because it seemed unlikely to matter in practice. Yea, it is an operational reality built into the daily schedule of the most sophisticated crewed facility humanity has ever placed in orbit, a facility whose every system was designed with redundancy and careful margin. And even that margin requires active management when the station crosses through this specific patch of weakened sky. Think of it like driving through a tunnel where the signal drops out. But the signal in question is not mobile phone coverage. It is the planet's protection against space radiation. Outside the tunnel, on both sides, the field is at full strength, and the charged particles are redirected before they can reach you. Inside the tunnel, the deflection is reduced, the particles penetrate deeper, and anything sensitive to that kind of bombardment has to be managed accordingly. The ISS drives through that tunnel several times a day. The tunnel is not shrinking. It is expanding, and the signal inside it is getting weaker, and there are now signs that it may be developing a second minimum, that what was one region of weakness is beginning to resolve into two separate centers of reduced field strength, as though the anomaly is not merely persisting, but reorganizing itself into something structurally more complex. The reversed polarity patch that produces the South Atlantic anomaly originates in total darkness beneath the South Atlantic, deep in the outer core, where a region of the fluid iron is generating magnetic flux in the opposite direction from the dominant field above it. Not weaker in the same direction, reversed, pointing the opposite way. And because the field that reaches the surface above that region is the sum of the dominant flux flowing upward and the reversed flux pushing back against it, the result at the surface is subtraction rather than addition, a cancellation that produces the weakness you can measure from orbit. The reversed polarity patch originates in total darkness beneath the South Atlantic, in a region of the outer core where the flow patterns that generate the dominant planetary field are locally disrupted, where the convective currents that sustain the field have organized themselves into a configuration that works against the global pattern rather than with it. And here is where the partition that most people carry between the magnetic field story and the rotation story stops being a valid way to organize the information. The outer core is a single fluid system. The flow patterns within it do not have separate effects that operate independently of each other. The same changes in outer core convection that alter the angular momentum transfer between the core and the mantle, the electromagnetic coupling that has been driving the surface rotation anomaly measured since roughly 2016, are the same changes that alter the geometry of the field that the outer core generates. These are not two separate processes that happen to share the same location. They are different expressions of the same process. The rotation anomaly and the South Atlantic anomaly are different symptoms of the same disease, the same reorganization of fluid motion in the same body of liquid iron. One symptom visible in the microsecond precision of atomic clocks tracking the length of a day, the other visible in the radiation dosimetry logs of the International Space Station. Different instruments, different phenomena at the surface. One origin, 3,000 kilometers below. The South Atlantic anomaly is a window into one region of weakness. But the question that follows is harder. Is the entire shield declining? The window is the South Atlantic anomaly, but a window shows you what is happening in one room. And the question that has been building since the first measurements were taken is whether what is visible in that one room reflects what is happening throughout the entire structure. And the answer, drawn from 2 centuries of magnetometer readings collected on every continent and in every ocean, is that it does. At the global field, the full planetary shield, measured not just above the South Atlantic, but everywhere, averaged across the entire surface, has weakened by roughly 9% since the early 19th century. 9% sounds like a rounding error. It sounds like the kind of variation that sits comfortably within natural fluctuation, the kind of thing you note in a data log and return to in a decade. But 9% of a planetary magnetic field is not a small quantity, and the rate at which it is declining is faster than the average rate observed during stable non-reversal periods in the geological record. The field is not fluctuating around a baseline. It is trending downward from one, and the trend has been sustained across the entire period of reliable measurement. We have looked at each layer separately, and moving from the inner core outward through the mantle to the surface, through the ice sheets to the oceans and the atmosphere, through the South Atlantic anomaly to the global field. Now comes the part that researchers find genuinely difficult to communicate without either understating the science or crossing into alarm, because the numbers individually are each defensible, each carefully sourced, each the product of instruments and methods that have been independently verified. But what happens when you stop looking at them individually is something different from what any single number can convey. The geological record contains 2 categories of magnetic field behavior that matter here. The first is a full reversal, in which the dominant polarity of the entire planetary field flips. North becomes south, and the compass points the other way for the duration. The last full reversal, called the Brunhes-Matuyama boundary, occurred approximately 780,000 years ago. The average interval between full reversals, calculated across the deep geological record, is somewhere between 200,000 and 300,000 years. That means, by the straightforward arithmetic of statistical averages, the current period without a full reversal is already 2.5 to nearly 4 times longer than average. That is not a statement about when a reversal will happen. The geological record shows enough variability in timing that no specific prediction is responsible. But it does mean that framing the current state of the field as comfortably stable against historical context is not supported by the record itself. And the record says this interval is unusually long. The field says it is actively weakening. Those two facts belong in the same sentence. The second category of magnetic field behavior is called an excursion. Not a full reversal, but a severe weakening and partial reorganization of the field without a complete polarity flip. The best documented excursion in the recent geological record occurred approximately 42,000 years ago and is called the Lachamp excursion. What researchers have recovered from ice cores, from tree rings, and from cave sediments around the world is a consistent signal. During the Lachamp, cosmic ray flux reaching the surface increased sharply. The field dropped to a fraction of its normal strength. The shielding that intercepts high-energy particles from deep space was substantially reduced, and the physical evidence of that increased bombardment was recorded in isotope ratios preserved in ice and biological material across the planet. The same cosmic rays that atomic clocks aboard the ISS are currently being partially shielded from, the same particles that the South Atlantic anomaly already allows to penetrate more deeply, reach the surface in significantly greater quantities during the Lachamp, and the evidence of that increased flux is chemically readable in ancient ice drilled from Antarctica and Greenland thousands of years later. The Lachamp period also correlates, though the causal chain is debated, and the honest answer is the mechanism is not fully resolved, with climate disruption and with the disappearance of megafauna populations in multiple regions. The correlation exists in the record. The causation is not established with certainty. Both of those things are true simultaneously, and the record deserves to be described as it is rather than simplified in either direction. During a reversal transition, not the steady-state field, but the transitional period when the field is reorganizing from one dominant polarity to the other, the global field strength is estimated to drop to somewhere between 10 and 20% of its normal value, and to remain at that reduced strength for a period of thousands of years before rebuilding. Not weeks, not a solar cycle, thousands of years. That is the context in which 9% of decline since the 1800s and an anomaly expanding across the South Atlantic belong. And now here is the part that is genuinely difficult to communicate without either understating the science or crossing into alarm. Because what follows is not a rhetorical device, and it is not cherry-picking. It is a timeline. Take 7 independent measurement systems tracked by different instruments operated by different institutions using different physical principles, and ask a single question. When did each of them depart from its prior baseline behavior? The inner core seismic signature, tracked through the differential travel times of seismic waves passing through the Earth, shows a change in relative rotation rate beginning around 2009 to 2010. The outer core circulation, inferred from the geometry and motion of magnetic flux patches at the core mantle boundary, shows reorganization in the same window. The surface rotation rate, measured by atomic clocks and very long baseline interferometry, it began its anomalous acceleration trend around 2016, consistent with the years to decades coupling delay between core dynamics and surface expression that the physics of electromagnetic coupling predicts. Greenland ice loss, tracked by the GRACE gravity satellites, shows a measurable step change in the rate of mass loss around 2012. The South Atlantic anomaly minimum intensity, measured by satellite magnetometry through the ESA swarm mission and its predecessors, shows accelerating decline through the mid-2010s. Arctic sea ice extent, tracked by passive microwave satellite sensors since the late 1970s, reached its most anomalous departures from the long-term trend in and around 2012, and AMOC strength, the Atlantic Meridional, overturning circulation reconstructed through proxy records and direct measurement arrays, shows a transition toward its current weakened state through the mid-2010s. 7 systems, 7 independent measurements, 7 different instruments operated by 7 different communities of researchers with no coordinating authority and no shared methodology. Plot them on the same timeline, and they do not scatter randomly across the decades. They cluster, they converge. The departures from baseline are not uniformly distributed across the period of the satellite era. They accumulate in the same 10-year window, roughly 2010 to 2020, yes, with individual signals arriving in a sequence consistent with the physical coupling delays that the underlying science predicts. The deep core first, the surface rotation years later, the surface expressions of ice and ocean and atmosphere trailing behind in the order you would expect if a signal were propagating outward through a coupled system rather than appearing independently in each layer by chance. The probability that 7 systems with independent physical drivers depart from baseline simultaneously by coincidence is vanishingly small. That is not a rhetorical intensifier. That is the standard language of signal detection, of the same statistical framework used to distinguish genuine correlation from noise in any domain where coincidence must be formally ruled out. And when 7 lines on a single graph all turn at the same time, the null hypothesis, that they are unrelated, requires a level of coincidental alignment that the mathematics of independent probability distributions does not support. 7 systems moving together in the same decade is not 7 stories. It is one event, expressed through 7 instruments, each sensitive to a different aspect of the same underlying reorganization. When 7 systems that underpin the planet's physical behavior start moving together, is it coincidence? Or is something deeper speaking through all of them at once? 3 groups of researchers have tried to answer that. And what is genuinely difficult about their work, genuinely hard in the way that only problems operating at a scale that dwarfs any experiment humanity can design are genuinely hard, is that they do not agree on the mechanism, and yet they converge on the same conclusion. The first model is what researchers sometimes call the core-dominated interpretation. In this reading, the primary driver of the shift is the internal dynamics of the deep Earth, the inner core's changing rotation rate, the reorganization of outer core circulation, the electromagnetic coupling between those fluid motions and the mantle above. The prediction that falls out of this model is cautiously stabilizing. If the core system is the primary driver, and it is now in a phase of adjustment following a change in relative rotation, yet the surface expressions, the acceleration of Earth's spin, the shift in polar motion, the changes in the geomagnetic field, should trend toward a new equilibrium over decadal timescales. Not the old equilibrium, a different one, but something that settles, at least partially, as the deep system finds its new configuration. The second model emphasizes ice and atmosphere coupling. In this interpretation, the reorganization of the climate system, the accelerating loss of ice mass from Greenland and Antarctica, the weakening of the jet stream as Arctic amplification reduces the temperature gradient that drives it, the changing distribution of atmospheric mass across seasons and latitudes, is feeding back into the rotation and wobble of the planet itself in ways that amplify rather than stabilize. The polar drift that accelerated to roughly 17 centimeters per year after the year 2000, a rate with no recorded precedent before that point, reflects this interpretation's strongest evidence. The planet's rotational axis is being pulled toward Greenland, partly because Greenland is losing mass at a rate the geological record has not seen in human history. If Arctic warming continues on its current trajectory, this model predicts that the signals will not soften, but will instead track the climate trajectory, which means the direction of change is tied to how aggressively the atmospheric system continues to reorganize. The third model centers on the electromagnetic dimension, the weakening of the geomagnetic field, the expanding South Atlantic anomaly, and the possible early stages of a field transition that the paleomagnetic record suggests is overdue. In this interpretation, the field's continued weakening will drive continued change in the coupled system until the field itself either recovers or completes a transition to a new orientation, a process that the geological record suggests takes thousands of years even in its faster expressions. These three models are not mutually exclusive. Researchers working on each of them are not claiming the others are wrong. What they are disagreeing about is which forcing dominates, and that distinction matters enormously for what happens next. But here is what they do agree on. And this is the point that the argument has been building toward since the very first measurement. None of them predict that the system returns to the state it was in before 2010. Not one. The core-dominated model predicts stabilization at a new equilibrium, not restoration of the old one. The ice atmosphere model predicts continued departure in the direction of the current trend. The electromagnetic model predicts continued departure until a geological scale process resolves itself. Three competing frameworks, three different mechanisms, one shared conclusion. The baseline is gone. The technical term for this is non-stationarity. It sounds like jargon, and it is, but what it means in plain language is precise and important. The statistical properties of the system are changing. The average is moving. Yes, the variance is moving. The historical record that every engineering standard, every risk model, every safety margin was calibrated against is no longer a reliable predictor of what the system will do next. This matters in ways that go far beyond geophysics, because every piece of infrastructure that human civilization operates was designed and calibrated under the assumption of stationarity, the assumption that the planet's behavior over the last 10,000 years would continue to describe the planet's behavior over the next century. That assumption has a name. We call the period it describes the Holocene. The Holocene began roughly 10,000 years ago, as the last major glacial period ended and the planet settled into the conditions that allowed agriculture, then cities, and then the entire architecture of industrial civilization to develop. 10,000 years is, by geological standards, an unusually quiet and stable interval. The magnetic field was not in transition. The ice sheets were not undergoing rapid reorganization. The rotation rate and polar position were varying within narrow and predictable bounds. Every engineering standard in the world was built on measurements taken during this interval. The load tolerances of bridges were calculated using Holocene flood records. The drainage systems of coastal cities were designed using Holocene sea level baselines. The navigation databases that commercial aviation relies on are updated on a 28-day cycle, a cycle designed for a world where the magnetic pole moves slowly and predictably enough that a month-long update window captures all meaningful change. Civilization was not built to survive a geophysical transition. It was built to operate inside a stable state. Those are different engineering problems, and the difference between them is not a matter of degree. A house that was built to stand in calm weather is not merely slightly underprepared for a hurricane. It was designed for a different set of forces entirely. Consider what non-stationarity means for specific systems, because the abstract claim only lands when you follow it into the engineering. Our power grids maintain synchronization across enormous geographic distances by matching the phase of alternating current to a shared standard, 50 or 60 cycles per second, depending on the region. When phase alignment drifts beyond threshold, automatic disconnection cascades are triggered to protect equipment, and those cascades can propagate across interconnected networks faster than human operators can respond. The tolerances that define those thresholds were set based on the stability of a Holocene grid. Hospital linear accelerators, the machines that deliver precisely targeted radiation to tumors, coordinate their beam delivery with a patient's breathing cycle, firing in windows measured in fractions of a second, timed to sub-millisecond precision. And the timing infrastructure that makes that coordination possible depends on atomic clock signals that are themselves referenced to a rotating Earth whose orientation must be tracked and corrected continuously. Financial exchanges process millions of transactions per second, each carrying a microsecond timestamp that determines legal priority. And the integrity of those timestamps rests on a timekeeping infrastructure calibrated to a planet whose rotation rate was assumed to be varying only within historical bounds. The fact that financial regulators have classified their modeling of leap-second elimination and field transition scenarios is not a bureaucratic detail. It is an acknowledgement that the people responsible for those systems understand that the margins were sized for a Holocene planet. And all of it is running. The navigation databases cycling on their 28-day schedules, the grid phase monitors holding their thresholds, the accelerator timing chains, the exchange timestamps. All of it is running on assumptions whose underlying foundation is now being renegotiated by processes that do not consult engineering standards. The geological record contains one event that illustrates what simultaneous destabilization of foundational systems can produce at full amplitude. Approximately 450 million years ago, during the late Ordovician period, roughly 85% of marine species were eliminated in what is now recognized as one of the 5 largest extinction events in the history of complex animal life on Earth. The specific mechanisms involved climate reorganization, glaciation, a sea level change, and disruption to the chemical gradients that marine ecosystems depended on. Not a single cause, but a convergence of pressures that the biological systems of that moment were not equipped to absorb simultaneously. The lesson from the end Ordovician is not that the Earth was destroyed. The Earth recovered. The lesson is that the recovery happened without the ecosystems that existed before the transition. The safety margins of the biological systems operating in the Ordovician oceans were sized for the conditions of the Ordovician. When those conditions changed faster than adaptation could track, the margins were not exceeded gradually. They were exceeded catastrophically. The planet that emerged from that transition was stable again. It was just not the same planet. Yet the question is no longer whether change is happening. That is settled. The question is speed. And the honest answer is that the uncertainty is increasing, not because the measurements are getting worse, but because better measurements reveal tighter coupling than models assumed. What is certain can be stated plainly, and it deserves to be stated plainly after everything that has been laid out here. The Holocene, that 10,000-year window of unusual geophysical calm that allowed agriculture, cities, navigation, and every instrument of modern civilization to be built on assumptions that were never written down because they never needed to be. That period is in transition, not ending in the dramatic sense, not collapsing on a timeline measured in years, but shifting immeasurably and across multiple independent systems simultaneously toward a new equilibrium whose character we cannot yet read with confidence. All 3 modeling groups, the ones working from the core outward, the ones working from the ice sheets downward, the ones working from the electromagnetic data inward, agree on that single point. The new equilibrium will be different from the old one. How different, and over what timeline, are the questions that remain genuinely uncertain, and it is important to hold that word carefully. Genuinely uncertain does not mean unknowable. It means the data we have collected so far does not yet constrain the answer tightly enough to choose between outcomes. There are 3 questions that sit at the center of what is not yet resolved. And the first is whether the inner core reversal detected in the 2023 seismic analysis represents a true change in rotational state or a measurement artifact that will be refined away as the global seismographic network, which operates more than 150 broadband stations distributed across the planet's surface, accumulates more data from more events. The Southern Ocean remains the largest monitoring gap in that network, and gaps in coverage are not neutral. They are places where the answer could be hiding. The second question is whether the magnetic field is tracking toward a full polarity reversal or toward something shorter and less complete, an excursion, like the Lachamp event 42,000 years ago, after which the field recovered. Yet the data does not currently distinguish between those trajectories with enough precision to say which path is more likely. The third question is whether there is a threshold somewhere in the coupled ice-ocean atmosphere system at which the feedbacks stop being linear and become self-reinforcing in a way that removes human timescales from the equation entirely. That question is the one that carries the most weight and also has the least definitive answer. And yet, the instruments are running. The data is arriving. 3 swarm satellites are tracing the field's evolution from low Earth orbit. The GRACE follow-on spacecraft are measuring mass redistribution across the planet's surface with a precision that would have seemed implausible a generation ago. Our VLBI arrays on multiple continents are timing radio signals from quasars, billions of light years away, to track the precise orientation of the Earth in space. The global seismographic network is listening. Every significant earthquake that occurs anywhere on the planet passes through the instruments, and each one carries information about the interior that no direct measurement could ever reach. The planet is the experiment. The timeline is longer than any research career. That is not a comfortable framing, but it is the honest one, and there is something clarifying about it once you stop resisting it. The understanding that the question being asked here is larger than any individual effort to answer it, and that what we have are measurements of a process already underway, and not a forecast we can simply refine into certainty by running the model one more time. The planet is not broken. That is also worth saying plainly. It is not dying in any sense that the geological record would recognize. It has moved through magnetic reversals and excursions and orbital perturbations and the kind of glacial cycling that buried the place where you are lying right now under kilometers of ice, and it has emerged from each of those transitions into a new stable state that supported complex life. The question has never been whether the planet persists. The question is always what persists with it, and whether the systems that were built inside a particular stable window are resilient enough to operate across the transition to a different one. Civilizations are not geologically durable structures, and they are calibration-dependent structures, tuned to the conditions that existed when their foundations were laid, and somewhere 5,100 kilometers below your feet, in total darkness and under pressures that no human instrument has ever survived long enough to measure directly, at temperatures that approach the surface of the sun, iron is flowing. It has been flowing for 4 billion years without pause, without light, without any reference to anything happening on the surface above it. The patterns in that flow are what generate the field that makes navigation possible, that deflects the particle streams that would otherwise strip away the chemistry of the atmosphere, that has been quietly holding the conditions of the surface within the bounds that complex life requires. Those patterns are changing. The instruments are running. The data is arriving. And the answer is already encoded in the way the iron moves, in the convection cells and the reversed polarity patches and the coupling delays that take years to travel from the core to the surface, already written, already in motion, already producing the signal. We just have not finished reading it yet. If you could ask the planet one question, just one, what would you most need to know?